Hello, everybody. I hope everybody is feeling well. It's taking care of yourself and the others. And today we have another seminar, and we have a pleasure to have here another member from the Tübingen group. So Tübingen is we are having a very strong collaboration in the last few years. And today we have Anna Bitt, Tabe Penzlin. Is that okay?
Yeah, Anna's fine.
And she got a bachelor's degree and Master of Science in University in Heidelberg, and a PhD just recently, a couple of months ago, in Tübingen. And she's going to Imperial College in London. So, and she's an expert in binary systems, exoplanetary binary systems. So, with several papers published already. So, the podium is yours. You are welcome.
Thank you. Okay, let's share the screen again and hope that it works. 1 second. Yes. Okay. Did it? Okay. You see the presentation? Okay.
Yes, perfect.
Perfect. Cool. Then let's just jump into this. So I'm, as already mentioned, I'm working on planets and circumbinary disks, which is maybe also interesting to you because we have a lot of objects that can have a lot of different orbits, but I'm actually coming from the more complicated side of hydrodynamics, and we will just walk our way through this. So let's first think about, if we think about a planet around a binary, that is what a planet around a binary looks like, right? So this is the name of the planet, obviously. And yeah, this is actually the projected orbit from the Kepler data of this planet. So that I would be this year, right? That's exactly the kind of thing that I want to talk about here. And so to actually end up with a planet like this in a nice orbit that is ideally almost habitable, just a horrible desert planet, we need to move all the way through an evolution of a planet. And this is what I will now try to show you, how you get from just the disk and then the planet in the disk towards having the final orbit of the planet there in the place that you would wish to have the planet in. So let's start with the more complicated hydro and move to the orbit later. So a binary has a circumbinary disk like this one. This is a scattered light image of a circumbinary disk, and what you can see here, this dark region is actually where you have no scattered light, meaning that it is a very empty region because light scattering is, well, you don't need a lot of, it's very obliquely fixed, so you don't need a lot of dust anywhere to scatter light. When it's dark, it really means there's nearly nothing. But you can also see you have these things coming into the, so you have a large inner cavity. Then you see you have some material going in here. You can see my mouse, right? Hopefully.
Yes, you can. Yes, you can.
Thank you. And then if you look at the outer parts of the disk, just where you see the scattering, then you also see that there are some spirals here. So these are the features that a real observed circumbinary disk should exhibit. And this is what we need to also accomplish with our simulations if we want them to be more or less realistic. Now let's see how we can simulate such a system. So we will start with just a short simulation just to get a basic idea, where we have the two stars. Here is the secondary star, this is the primary star, and we have some surface density, so just gas in the background. It's in a log scale, so well, you will see any tiny amount of gas, and when it's black, there's really no gas whatsoever. And when I just let it start after initializing it with this nice symmetric shaped distribution, this is what happens. So very quickly, the two stars will start, even within their first orbit, to sweep up the gas in proximity and clear out their own orbit. And as they progress, they will clear out slowly more and more here in the disk towards creating this kind of cavity, right? Because we saw this large inner cavity. Now that just takes a bit, a while. And while they do this, we also see that they fling out material over and over again that later will be helping us to form the spirals that we saw. So this is just like a few tens to hundreds of orbits, what we have here. So it's quite early to say that this is the concluded picture, and we want to understand now what would a converged simulation look like that ran as long as needed to really get a disk that is in a quasi-stable state. So in the second simulation, you will see the time up here. It will now be in tens of orbits in each time step, so much faster, and you will see how the inner cavity will now grow. Here, the two stars are outside of the domain. So the white part is not simulated. The stars, however, are implemented as n-bodies. But the gas that goes into the white domain is just lost to the system. So what you directly see is, okay, you do get these outer spirals. This is now not a log scale, but just a normal gas scale. And as the time progresses, this inner cavity becomes eccentric and ever so slowly larger, actually. It started a bit smaller, and now it's getting somewhat larger and larger over time. And roughly after like 10,000 binary orbits, we reach a quasi-converged state of an eccentric inner cavity that is as large as a semi-major axis of 3 to 6 binary separations. So this is really large, the MC region in here. And now you see it's just precessing slowly around the binary, but overall the pattern stays stable. So once more, looking at these features now in smaller time steps after they converge, you can see here now without the log scale, just for the outer parts of the disk, that you have these spirals, and these spirals are following the motion of the stars in the outer part. Just with every rotation, you create the spiral here again and again and again. This is how you get the spiral in the outer part of the disk, like the inner part of the disk, but beyond the cavity, of course. And then in the log scale, you can now actually see how on the one side gas will get flung out, and on the other you will get gas accreted, even with these kind of infall patterns here. They vary over time, but from time to time you just get these infalls, which is again also what we have seen in the observations. This is what the dynamics inside the circumbinary disk looks like overall. Now, there is a few things if you simulate hydrodynamics that are important, and one of the most important parameters is that you can change the viscosity, and changing the viscosity will affect the structure of your cavity and of your disk, of course. And so you have here a very high viscosity and here a very low viscosity, meaning that the radial drift of gas inwards is very fast here and slower here. And you can see that with reduced viscosity, the eccentricity of your inner cavity reduces, and you get also this more ring-like feature near the edge, so at the inner part of the disk. For those of you, I don't know how familiar you are with the concept of the alpha viscosity, the property denounced here. The idea is that in order to explain viscosity, we will not have enough viscosity by simply considering a molecular viscosity as you would have just in water or something like that, or then in the gas that you have in a disk, but you need a much larger viscosity to explain the amount of accretion that happens in an accretion disk. And to explain that, you could consider gas parcels as kind of macroscopic particles that are bound as turbulent eddies, like here. And then you can just describe a viscosity by the relevant length scale and the relative, the relevant velocity, which is the sound of speed, and the scale height. And then you say your viscosity has to be smaller, like your disk has to be, the eddy has to be smaller than the disk scale height, and the velocity has to be smaller than the speed of sound, because this is like the limits of your system. And then you just prescribe this alpha parameter, which is now a very small number, and usually it has to be in the order of 10 to the minus 3 to 10 to the minus 5 to match what we see in observations as accretion through the disk. Now the question is it a valid assumption to assume that you have some turbulence in disks going on? There are various instabilities. And for binary disks, actually, the binary in itself already produces quite a turbulent steering up environment, as you can see. So this is the gas, a dust density inside a disk, and you can see by the steering up motion here that this is already quite turbulent. So assuming that we have a large enough viscosity there to justify this alpha is definitely possible. So now we can also kind of use this alpha as a parameter and map exactly what the cavity of our, if we go back up here, so what this white dashed line, this cavity looks like for different alpha parameters, and also for binaries that have a different eccentric orbit. And this creates you this map. So the viscosity will increase from here to here, and the eccentricity of the binary will increase from here to here. And brighter color means that you have a larger cavity for this plot, and brighter color here means that the cavity will become more eccentric. So actually, higher eccentric cavity means that you have a very uneccentric binary, and that you have a somewhat high viscosity, if you just want to kind of simplify the information in this map. Now, so far I only talked about the disk, but I wanted to talk about planets in the disk, so let's go back to our nice planet here. The Kepler mission and now the TESS mission have discovered a few, around a dozen circumbinary planets, which are all these dots here. And when you look closely, you see that we have the semi-major axis on the x-axis and the eccentricity on the y-axis, and they all assemble around a very tiny spot in semi-major axis. So they are actually tightly packed to a specific location, no matter in which binary they are, binary system they are. And you can also see that the eccentricity only goes up here to 0.15. So they are also all quite uneccentric. And this is actually quite interesting that all these binary planets that we have observed so far are that are close in near the stars, they are very comparable. So that might suggest that they all might have formed or might have gotten into this orbit by the same mechanism. As I already told you, the inner part of the disk is quite turbulent, and turbulence will prohibit you from forming planets in this region. However, you can still migrate into the inner part of the disk and even maybe beyond. So let's talk a bit about what planet migration does. Generally speaking, and we have two most important types of migration. We have type 1 migration, where you have a planet that is not quite able to open a gap and then just creates a spiral epicyclic wake that will transfer angular momentum, which will lead to an inwards migration of type 1. So you could stop this migration by not having gas anymore in the vicinity of the planet, for example. And then there's type 2 migration, where you have a planet that is so heavy that it clears out a full gap. And in this type of migration, the planet can migrate due to two effects. Either the planet can migrate because the gas in the disk is accreted, and then so the gap shifts and shifts the planet with the moving gas as a gravitational torque, or the planet can be shifted due to differences in the torque from the densities inside and outside of the planet's orbit. So this would also stop if you just took away all the density that is here and only had density here. Then the gravitational torque would only appear on this side, and the planet would get pulled back towards this side. So this is how you could stop a planet migration, meaning for our cavity, or the inside of our cavity will be a great stopping block for planet migration. Or if you reach just a steep density gradient, that can also be a stopping block for migration. And one important thing for this is, if we come back to the viscosity part, if the planet needs to open a gap, the viscosity will work against this. The viscosity will flow in material into the forming gap. So viscosity, high viscosity, will lead to an inflow through this gap and fill up this gap fast. So it's harder for a planet to open a gap if the viscosity is higher. So what does that lead to for a planet? You have seen this picture before. This is the disks that we have already simulated for different viscosities. So here we have a very high viscosity, and here we have a very low viscosity. Now, with these disks, we also add a planet each time in these disks. And as I explained, if you have a high viscosity, it's harder to form a gap. If you have a low viscosity, it should be easier to form a gap. And this is what you will now see. If you look at this panel here, you can definitely see that there is not really a gap forming. Here you see that there is some lack of gas density, so the color in the planet orbits becomes somewhat darker, but the gap is not very deep. While in the last panel with the lowest viscosity, you see that the planet has passed all the way through the disk and entered into the inner cavity, and there it's now stopped because the gravitational torque will just now pull it back towards the disk. While in the other cases, the disk kind of stops the motion of the planet already. Now, this was one of the examples that we looked at. As I said, there are about a dozen systems. Here are now a sample of 8 of the systems that have been observed so far. And these systems are arranged in some order. So on the top here, you will have binaries that have an intermediate binary eccentricity, as I have shown you in the map. If you have an intermediate binary eccentricity, the cavity, as you can see, is quite circular. The reason why this cavity is not quite as circular is because for this one simulation, we used a higher alpha value than for the other simulations, because the planet mass here was already high enough to migrate further than in the other cases. For the lower part, we have here 3 systems that have a very small binary eccentricity. And if you remember the map, that means that you get the most eccentric inner cavity possible. As you can see, they are more eccentric than in the upper panel. And then the last system here is one system where you actually have a very eccentric binary that also creates eventually a very eccentric cavity. It's just there's just this single case where you have this. So if we now put the planets in, let them migrate, and wait for a while for the simulation to converge to a stable orbit, then this is what we get out. In the upper row, we find that the planets always migrate inwards into the cavity. We find that the planet's orbit is about 3.6 binary or 3.5 binary separation in each case, which is, if we look back at the plot of the observed binaries planets, exactly the semi-major axis that the planet should have from the binary. In the lower panel, however, we see that the planets stay embedded in the disk, are also on an eccentric, more eccentric orbits, let's say that, and are further out at like 4 to 5 binary separations, or even 6 in the case of the very eccentric binary. And in these cases, we don't quite reach the observed orbits with the simulations. So what does it look like overall? Here we have the real observational data of the planet, so semi-major axis and eccentricity. And with the simulations, you see the bright spots are now where the simulation planets end up and are stopped by the gas disk. You see, you have these 3 systems where it's a bit off, and then you have this block where you actually can match the observations fairly well. Now, in a dynamic sense, if you track the time evolution of the semi-major axis of the planet and the eccentricity of the planet, then you see they migrate in quite fast, then they hit the inner edge of the disk, get slowed in their migration, and then slowly, and even with some jumps, proceed to go through the inner part of the disk into the cavity. These are now all these systems that have a binary eccentricity that makes the disk not quite as eccentric and allows the planet to pass all the way through to reach the observed orbits. And for those systems where this doesn't work, this is what it looks like. Again, initially you have very fast migration towards the inner edge, and then it just cuts off. The planet somehow gets embedded in the disk and just stays there stably. this one yellow system is almost at the location where it is observed, just not quite in the threshold that we set for ourselves back in this study that we did back then. So it was also not counted as a success. Now, here's another video of these more complicated cases where the planets do not quite reach the orbit, and you can see how they are still staying embedded in the disk. And the interesting thing is also, while they are embedded in the disk, their precession around the binary aligns with the precession of the cavity in the circumbinary disk. So planets are now bound in the circumbinary disk in the cases when the planet is still embedded in the circumbinary disk. They are somehow dynamically bound. Now we come to some newer things that are a bit more, let's say, unpublished and just I just explore recently. We can look at multi-planet systems, as we have seen in the very beginning. The Kepler 47 system, for example, is a three-planet system. And so the question is, can we get multiple stable planets in a circumbinary configuration? So we got in here 2 planets in the outer disk. Now, if we go in, you can see one here and one here. They're moving in, and as they move in, they also clear their orbits, and then eventually they end up inside the inner cavity, both on a stable orbit. And I was just discussing this with Richard Nelson. Apparently even most likely in a resonant orbit here, like a 2-to-3 resonance or something like that. Now, if we look at this just in a diagram, we have the time over the semi-major axis for just the one planet, which just migrates through the disk and ends up in its stable orbit. If we now have the 2 planets, they migrate in together and then stay both in a stable orbit. One thing that doesn't work is if you have a lighter planet orbiting in first and then a heavier planet coming after it, the second planet will migrate faster than the first one. It will cross or come too close to the orbit of the first planet and cause the first planet to be ejected. So you can, like, it's difficult to have a lighter planet first and then a heavier planet following this. But if you have a heavier planet first and then a lighter planet following it, you can again find a stable orbit, at least for this system. So with this information, I tried another test where the planets are now a third of the mass. So we had the one planet case that was quite stable. So the planet just moved through the disk on a bit bumpy way, but eventually reached a stable orbit. If I now took 2 of the same mass planets, then they both migrated through the disk, but then got trapped into some, here in 1-to-1 resonances and some other interesting interaction behavior. If I got then took 3 planets, it got even worse. They one after another ejected each other, and with 4 planets, they just behaved like the 2-planet case, but because they started to eject each other after a while. So apparently to get multiple planets in a circumbinary setting is a bit tricky to get them actually in a stable orbit, and it has to be carefully adjusted such that the planets do not kick each other while still not migrated to their final orbit. And then you get even these interesting phases if you do that. there was now specifically the Kepler 47 case. We found that this was one of the most difficult cases because Kepler 47 has a binary with a very low binary eccentricity, so the disk is actually quite eccentric. And with the mass of the planets that was observed, we couldn't get it really to match well the observations. But if we increase the mass tenfold, then the planet would just perfectly orbit in and finally reach the parking position that matched very well the innermost planet if we just put in this one planet that has 10 times the mass of the innermost planet. If we now took all 3 of the planets, put them in and let them migrate, and one got ejected and 2 of them managed to find a stable orbit, and all was good, as we had the case before. But now, if we had them with normal mass, but the innermost 2 planets had the same mass, the first one migrated in, but did not pass through the whole disk, got somewhere trapped in the disk, and then the second one orbited in and orbited exactly onto the same orbit and into a one-to-one resonance, as I will show you in a moment. Now, if you reduce the viscosity, the gap would be slightly larger. Then the second planet would push the first planet a bit in, which would be enough to force it to be scattered out of the system completely, and then only the second planet would remain. But now we will have a slight look at this specific, very interesting case where you have both planets orbiting in, getting damped by the disk into exactly the same orbit. So this is what it looks like dynamically. We had this for 2 systems, for Kepler 47 and for Kepler 413, because both of them have very small binary eccentricities. So in that sense, they're quite comparable. And as you can see, they also have, therefore, a very eccentric inner cavity. And you already see the first planet, the second planet in both simulations are still quite far out, as noted here and here. So here the second one is just coming into the simulation. And you can see they are getting closer. Now these 2 got into resonance, and they you can also see that the orbits are crossing each other a slightly bit over and over. Now, also the second simulation had done the same. You also see that these orbits stay again aligned with the cavity. So they are bound to the motion of the disk as long as the disk is there. If you look at it in the mean motion, mean longitude over the semi-major axis, you see some patterns that are actually a kind of a horseshoe orbit. If you look at it this way, it becomes clearer. So you have a periodic crossing around the 2 Lagrange points, which is it's a bit complicated in this case because you also have eccentric orbits, but in this sense you can see this horseshoe orbit. In this, for Kepler 413, it's much clearer. Even you definitely can make out here a horseshoe, so you're really in a resonance, and the planets are never getting too close such that they should actually interfere with each other's in a more destructive way. And this is now all the data for a hydro simulation. But what happens now if we don't have a disk? Because as we have seen before, these 2 planets in one-to-one resonance exist as long as there's a disk, and they also precess with the disk. So if we don't have a disk, we can just continue that. We continued the same simulation, but just with n bodies. So it took out basically all the gas, or just put it into an n-body code and let only the n-bodies continue running. And what we found was that we here in the semi-major axis, here eccentricity of the two objects, you see them crossing orbits, but they stay perfectly in a stable configuration, swapping orbits over and over, but not actually kicking each other out. So we actually have the stable one-to-one resonance even without the disk. Now, in a very recent project, we were interested in if we can produce this with the hydro simulation, and if we can show that the one-to-one resonance we find in the hydro simulation is stable, can we reproduce this with an n-body simulation and figure out which one-to-one resonant planets would be stable around a binary. So first we just checked for a single planet in this figure here. This is for a single planet around a binary. Just the stable orbits are the yellow ones, and then where it gets blue, you get the planet ejected at some time. So, and you can see that you get less stability the higher eccentric your planet is, obviously, and you can also see that you have these tubes in this figure, which corresponds to resonances and like broadened resonances. And the red line is actually a curve that would be scaled linearly with the pericenter, because here we plot the semi-major axis, but if you normalize it to the pericenter, then this would just be a line. And this basically is a simple approximation to which orbits are stable. So you could actually just use this as an first estimate. And we did now the same thing also for the co-orbital configuration of planets. So for a one-to-one resonance of planets around a binary. So you see the blue in the blue region, all no planets can orbit. It's unstable for either one or two planets. In the gray region, it's stable for a single planet, but not for a one-to-one resonant planet. Now, in the yellow region, it's actually stable for one-to-one resonant planets. And this is now the interesting part, is actually you can find, even for very high eccentricities, still one-to-one resonant orbits, and they are in the pericenter even getting close to the binary. So even very eccentric planets that are both on the same orbit could have a stable orbit around a binary, which is now something that we are about to publish, hopefully soon. And yes, so this is basically our journey from the disk to the planets, and then finally to the configuration of planets. So what we have seen that the circumbinary planets, they all have this comparable orbits. They have low eccentricity, and they have a semi-major axis of 3.5 binary separations, which is just on the brink of being stable. So, and usually inside of the cavity in the disk. We have seen that if we have an eccentric disk, then the planets are stopped further out because they can't pass through the disk completely and are just trapped by the motion of the disk and in the same precession. And then we have seen then that if we lower the viscosity, that the planets can migrate further, because we go from type 1 migration to type 2 migration. And with type 2 migration, having this gap allows the planets to detach from the disk and orbit all the way through the disk into the inner cavity where we observe the planets. And then we have seen now in the most recent results that I'm still working on, that if you have multiple planets, you can slightly push through the whole disk with both of the planets and end up in stable orbits. But you can also scatter these planets out, and you can simulate the single planets that we have observed fairly well, as long as you have a moderate binary eccentricity. And then we can really reproduce the observations with the simulations that we have. And the last point that we just looked at is if we have one-to-one configurations, they are n-body stable, and there are ways with hydro simulations to actually produce them around a binary. And that would be all. So I'm happy to take any questions, and thank you for listening.
Okay, Anna, thanks for the very nice presentation. So now we are open for questions. Let me see. I think Barbara has set on one question here, but I don't know which slide was that. Can you make your question, Barbara?
Yes, sure. Hi, Anna. Thanks for
Hi.
your presentation. I have a doubt about the density of these disks.
Mm-hmm.
How much are you using, and how long the time of these simulations?
Okay. I have the scale. The scale is not. These simulations as usually locally isothermal, but of course for the planet later is important what you have in mass. The disk mass in total usually is about 1% of the binary mass combined. I mean, and so just the normal, I would say. So shouldn't be self-gravitating, but should also not be a very light disk. And the simulation times can just go here. So just for the planet itself, we simulate about 70,000 binary orbits. For the disks, I think it's also noted, usually, like, I took the picture at 25,000 orbits, but usually we simulated roughly 50,000 orbits just to really be sure that we see the converged behavior, because it is horribly important for a binary to really simulate long enough to have them converged. Exciting these eccentric modes takes a lot of time. They are long-lived, but also very slow in being produced. Yeah.
Okay, thank you very much.
Okay, Barbara. Any other question? Any comment? Well, I have one about the corbitals. You
Yes.
showed one example of horseshoe. Did you, for instance, in your one of the last pictures you showed about the corbitals, after that, where you found the stability regions? And what about what kind of corbitals you set? Can you think about, for instance, did you consider just simple dead pole orbs, just small?
Here.
Yes.
For these. So and full credit for this, by the way, to my student Stefan Adelbert, who's working with me on that. So for this one, we set the two planets across from each other, basically, so 180 degrees apart. And we actually tested out different configurations. So either aligned with the binary, anti-aligned with a binary, or just some other configuration. In the end, we settled on having the relative angle between the pericenter of the binary and the pericenter of the planet orbit being pi, because then you are in the most unstable configuration. But we had, I don't have it in the presentation right now. I might bring up the figure if you're interested. Just one sec. So the is here. Can you see my full screen or only the browser?
You stop the presentation and share again.
Yeah, sorry.
Oh, okay, yeah. Now you can see the screen.
Just here. Okay, let me try this concept picture. For some reason I can't, but I can. So you see this now? The figure? Yeah.
It's surviving. Okay, yeah, we can.
Yeah. So this is now for different relative angles between the binary and the planet alignment, orbit alignment, and we chose it to be here to have just the most unstable setting to compare this with. And then, even though we started them 98 degrees apart, we took a few examples to actually see that they are indeed on horseshoe orbits. You can't, of course, do this for all of the orbits. Wait a sec. This is now here. So this is, for example, one of them, just randomly drawn, basically. So, and they are started out, well, basically in L3, but they end up in a horseshoe orbit stably, and that is generally the picture for almost all random samples that we just picked. There's with one exception for a very weirdly very close in stable configuration that is just too close in to be considered really to but in the region where you really get stability, I think I'll just share my share the presentation again. There you generally have indeed horseshoe orbits in this sense. Does that make sense?
So you choose it to, when you say orbital sphere or resonance one-to-one, you are talking about horseshoe configuration. And the mass of the planets are the same? Or?
Yes. For this, we just, for now, we just took always exactly the same mass. When I did the hydro simulations initially, that led to the one-to-one resonant stable configurations, I played around a bit with the mass. That in some instances led to stable tadpole configurations. But again, we could also produce stable configurations there that where the mass would not be exactly equal. But in this case, there were a few configurations that ended up in tadpole if you did not take exactly the same mass. Yes.
If you take the same mass, the tadpole configuration is not the favorable one.
Yeah. If I take exactly the same mass, then I would not end in tadpole, but always in horseshoe. But if I have slightly different masses, then sometimes I would end up in a tadpole configuration.
Oh, I see. I see. So the masses would give preference to horseshoe or tadpole.
Yes.
No, okay. That's interesting. Yeah, I didn't know that. Okay, okay, that's interesting because we are doing some work
Mhm.
on orbitals of for exomoons.
Ah,
So and with masses, and we are facing this kind of study. So
mhm.
that's interesting. You said you are going to publish it soon.
I hope so. I hope so.
Okay.
We have actually newer, better resolved data for this plot, and it just needs to be somehow put into a nice figure, and then I think that should be the last step before publishing.
Okay, okay. So I'm looking forward to see these results. That's good.
Thank you.
Okay. Anybody else? Any further comment or question? No? So I think that's it. Thanks very much. It was a very nice presentation, a sort of review on on binaries, and very, very interesting. And I hope we see other works from you soon.
Very nice to be there, like here.
Yeah, they're here.
There, yeah, wherever we are
Yeah.
in
All
some
right.
virtual, nicely common room.
Okay, okay, good, good, good. So
Okay.
thank you very much. And now we have just finishing the seminars. We usually have a time for some